A solution's concentration tells us the amount of solute per solvent. A common unit of concentration is molarity, and molarity is found by taking the moles of solute divided by the liters of solution. Many first-year chemistry students have used this triangle to help them manipulate the variables in this equation. How this works: you cover up the variable that you are asked to calculate, and the orientation of the other variables tells you what to do with them. So, for example, if we want to calculate molarity, we cover that up and we see that we need to take moles divided by liters. If we want to calculate liters, then we cover that up and we take moles divided by molarity, and if we want to calculate moles, we multiply molarity times liters. Typically, second year chemistry students don't need to use that triangle, but it's there in case we need it. And the one reason I still like to show it, even for my AP chemistry students, is related to this problem that we're going to tackle next. What mass of magnesium nitrite is needed to make 3.25 liters of a 0.35 molar solution? You can see in this problem that we're asked to calculate mass. Well, mass is not in the molarity equation. In order to get to mass, we have to calculate moles first and then sort of jump out of the triangle to grams. This is why I like to show the triangle, even though I don't use it and most of my AP chemistry students don't use it. It still has a visual picture there of going from moles to grams. Similarly, if you want to get into the triangle from grams, you have to first calculate to moles and then you can work your way within the triangle. Let's write the formula for magnesium nitrite. Magnesium ion has a 2+ charge. The nitrite ion is NO2-. So the formula for magnesium nitrite looks like that. We first then need to calculate moles by taking molarity times liters. We've done that. 0.35 molar times 3.25 liters. That gives us 1.1375 moles of magnesium nitrite. And now, if you refer at the top of the screen to the triangle, you can see we now are at moles, and we're going to use that as a jumping off point to calculate grams. And to do that, we need to calculate the molar mass of magnesium nitrite. I've put here in the middle of the screen relevant elements from the periodic table. So according to our formula, we need 1 magnesium, and we're going to need a total of 2 nitrogens and a total of 4 oxygens. 24.3 plus twice 14 plus 4 times 16, and apparently that comes out to about 116.3 grams. The units of moles cancel, and we round to 2 significant figures, because in our problem we were given 3 sig figs there, we're given 2 sig figs there, so we should round to the fewest of those, 130 grams. Steps for properly mixing an aqueous solution. 1. In an appropriate container, pour water in so that you have perhaps 80% of your final desired volume. This is an approximate technique and takes little time. And when we say here appropriate container, that depends on what you're doing and how precise you need to measure. If precision isn't all that important, a beaker might be fine. An Erlenmeyer flask might be fine. If you're looking for quite a high degree of precision, perhaps a volumetric flask. In any case, you're going to put a good mass of water in that vessel before you add your solute. And I would state this at this point, that an appropriate container for mixing solutions is typically not a graduated cylinder. There's a beaker, let's say, and we're going to fill it up perhaps 80% of the way with water. Then we're going to weigh out the proper amount of solute, and we're going to mix it into the water. And finally, we're going to top off our solution to our final desired volume, and we're done. That's how you mix an aqueous solution. Let's try one more problem. What is the concentration of sodium ions in a 0.025 molar solution of sodium phosphate? Now, sodium phosphate is a strong electrolyte, which means it has ions in solution, it has dissociated 100%. So the sodium ion has a 1 plus charge. We've memorized that the phosphate ion is PO4 3 minus, which means that the formula for sodium phosphate is right there. When those bunches get into an aqueous solution, they are of course going to dissociate in a 3-to-1 ratio, 3 sodium ions for every 1 phosphate ion. Now, we're told in the problem that we have a 0.025 molar solution of sodium phosphate. But the question is sodium ion. So if we were to make a little analogy here, it might go something like this. If an Na3PO4 is represented by a tricycle, where the Nas are the wheels and the PO4 3 minus is the rest of the frame, then when that goes into solution, we're going to get 3 wheels, and you can see them here at the bottom of the screen, plus the frame. And if we look at the number we're given, 0.025 molar, if we change the order of magnitude a bit, let's say instead of 0.025, it's 25. Let's say we have then 25 tricycles. If we take all the wheels off, how many wheels will we have? And the answer is 3 times 25, which is 75. Similarly here, if the original concentration of the sodium phosphate is 0.025 molar, the concentration of the sodium ions will be 3 times that, 0.075 molar. Final thoughts on molarity. Molarity is the ratio of the number of moles of solute to the liters of solution. 2. When mixing a solution, start with a large volume of solvent, then add your measured solute, then top off the mixture to its final volume. The initial large volume of solvent acts as a good heat sink in case the later mixing is greatly exothermic. You can also think of the initial large volume of solvent as allowing plenty of space for the solute to spread out so it mixes evenly.